Around 252 million years ago, the Triassic period began after the biggest mass extinction Earth has ever known. Most living things had disappeared, leaving a world that looked empty and broken. The land was joined together as one giant supercontinent called Pangaea, and the climate was mostly hot and dry. Over time, new plants spread, strange reptiles appeared, and the first true dinosaurs quietly entered the scene. They were small at first, but they marked the beginning of an incredible story. The Triassic was also home to the earliest mammals, flying reptiles, and many other unusual animals. This was a time of survival, change, and new beginnings that shaped the future of life on Earth as we understand it. The Triassic period began about 252 million years ago, after the largest known mass extinction in Earth's history. This period marked the beginning of a completely new chapter in the story of life. The earlier disaster had removed a very large number of living things from both the land and the seas. Many forests disappeared, many ocean animals became extinct, and many groups of land animals were greatly reduced. The world that remained was very different from the one that had existed before. Large areas of land were empty, many habitats had lost their usual plants and animals, and surviving species had to adjust to difficult new conditions. The Triassic period became the time when life slowly recovered, and new groups of living things appeared. At the beginning of the Triassic, Earth was still recovering from the great extinction that ended the Permian period. Scientists believe that almost every part of the planet was affected. The climate had changed, the oceans had been disturbed, and many ecosystems had collapsed. The surviving plants and animals faced a hard struggle. Food was often limited, and many places were dry and hot. Even though life had become much less diverse, the species that survived carried the future of life on Earth. Over many millions of years, they spread into empty habitats and slowly rebuilt the natural world. The continents were joined together into one giant landmass called Pangaea. Instead of the separate continents that exist today, there was one enormous stretch of land surrounded by a single great ocean. Because this landmass was so large, many places were very far from the sea. Areas deep inside Pangaea often received very little rain. This created wide deserts and dry plains. Rivers flowed through some regions, but many parts of the land experienced long dry seasons. Weather patterns were different from those of the modern world because the shape of the continents strongly influenced wind and rainfall. The climate during much of the Triassic was generally warm. There were no large ice sheets covering the poles like those seen during some other times in Earth's history. Many places experienced high temperatures for long periods. Rainfall varied from one region to another. Some areas received enough rain to support forests and wetlands, while others remained dry for much of the year. Seasonal changes were common, and many plants and animals had to survive periods when water became scarce. The sky above the Triassic world would not have looked exactly the same as it does today. The atmosphere had different amounts of certain gases, and volcanic activity released additional gases into the air. Large volcanic eruptions sometimes covered wide areas with ash and lava. These events could affect nearby environments by changing the landscape and making it difficult for plants and animals to survive. Over time, fresh land formed from cooled lava, and life gradually returned to these areas. The oceans also changed during the Triassic. Many marine animals had disappeared during the Great Extinction, leaving empty places in ocean ecosystems. New groups slowly spread through the seas and began to replace those that had been lost. Coral reefs, which had been badly damaged, slowly started to recover. Shellfish, early relatives of modern squid and octopuses, and many kinds of fish became more common as marine life rebuilt itself. Recovery in the oceans took millions of years, and different regions recovered at different speeds. Plants played an important role in rebuilding life on Earth. They provided food, shelter, and oxygen for many living things. Early Triassic landscapes often had fewer forests than earlier times because many plant communities had been destroyed. Gradually, seed plants became more widespread. Conifers grew in many regions and formed forests where conditions allowed. Other plants, including cycads, seed ferns, and ginkgo relatives, also spread across different environments. These plants were able to survive under the changing climate and became important parts of Triassic ecosystems. Many of the first forests after the Great Extinction looked different from forests today. Trees often grew in areas with enough water, while dry regions supported smaller plants that could survive with less moisture. Along rivers and lakes, thicker plant growth provided homes for insects, reptiles, and other animals. Fallen leaves and dead plants slowly built up soil, making it easier for more plants to grow over time. Insects continued to play an important role throughout the Triassic. Many groups had survived the Great Extinction and continued to pollinate plants, break down dead material, and provide food for larger animals. Beetles, dragonflies, and many other insects spread into different habitats. Their presence supported food chains that became more complex as ecosystems recovered. Life on land was dominated by reptiles during much of the Triassic. Mammals had not yet become the leading land animals. Instead, many different reptile groups occupied important places in nature. Some walked on 4 legs, while others moved on 2. Some hunted other animals, while others fed on plants. Their bodies came in many shapes and sizes, allowing them to live in forests, river valleys, open plains, and dry deserts. Among the most successful animals of the early Triassic were relatives of ancient reptiles that had survived the extinction. Some of these animals developed powerful bodies and became important hunters. Others grew large enough to feed on tough plants. These species filled many of the ecological roles left empty after the extinction. Their success helped stabilize ecosystems during the early part of the period. The ancestors of crocodiles also appeared during the Triassic. Early members of this group looked different from modern crocodiles. Some were active hunters that ran on long legs rather than spending most of their time in water. They lived in different environments and developed a wide range of body forms. Over millions of years, this group continued to evolve, eventually giving rise to the crocodilians that survive today. One of the most important events during the Triassic was the appearance of the first true dinosaurs. These early dinosaurs were not the giant animals that many people imagine today. Most were relatively small and lived alongside many other reptiles. At first, dinosaurs were only one part of a much larger community of animals. They did not immediately become the dominant land animals. Their rise happened slowly over many millions of years as they adapted to changing environments. Early dinosaurs had bodies that allowed them to move efficiently. Many walked with their legs positioned directly beneath their bodies rather than spreading out to the sides. This body structure helped them travel over long distances and remain active. Some early dinosaurs ate meat, while others fed on plants. As time passed, they developed into many different forms, laying the foundation for the great variety of dinosaurs that appeared later. The Triassic also witnessed the appearance of the earliest known mammals. These first mammals were very small animals. They probably spent much of their time hiding from larger predators. Many were active at night, searching for insects and other small food sources. Their bodies had features that later became common in mammals, including different types of teeth suited for various kinds of food. Although they remained small throughout the Triassic, they represented the beginning of the mammal family that would eventually include many different species. Flying reptiles also made their first appearance during this period. These animals, known as pterosaurs, developed wings supported by a greatly extended finger. They became the first vertebrates known to achieve powered flight. Early pterosaurs probably fed on insects, fish, and other small animals. They nested on land and flew above coastlines, lakes, rivers, and forests. Their arrival added a completely new group of animals to Earth's ecosystems. The seas contained many remarkable reptiles as well. Some returned to the water after their ancestors had lived on land. These marine reptiles developed bodies suited for swimming and hunting in the ocean. Some resembled modern fish in body shape, while others had long necks or broad flippers. They fed on fish, shellfish, and other marine animals. Their presence showed how quickly reptiles adapted to life in different environments. Fish populations also recovered during the Triassic. Many species that had survived the extinction spread into new habitats. New forms evolved as ecosystems became healthier. Freshwater rivers and lakes supported different fish communities from those found in the oceans. These fish served as both predators and prey, helping maintain balanced food webs. Amphibians remained important during much of the Triassic. Many lived near rivers, lakes, and wetlands where water was available for reproduction. Some species grew to impressive sizes and hunted fish or smaller land animals. Their survival depended on suitable freshwater habitats, making wetlands especially valuable parts of Triassic landscapes. As millions of years passed, life continued to become more diverse. Empty habitats created by the Great Extinction slowly filled with new species. Evolution produced fresh body forms, new feeding habits, and different ways of surviving. Some groups disappeared while others became more successful. This steady process shaped the changing ecosystems of the Triassic world. The movement of Earth's crust also continued throughout the Triassic. Although Pangaea remained joined together for most of the period, forces beneath the surface slowly began to pull parts of the giant continent apart. Cracks formed in some regions and volcanic activity increased along these developing rifts. These early changes eventually led to the breakup of Pangaea during later geological periods, creating new oceans and separating the continents. Changing landscapes created many different habitats. River systems shifted, lakes formed and disappeared, deserts expanded or shrank, and forests spread where rainfall became more reliable. Animals and plants constantly responded to these environmental changes by moving into new areas or adapting to different conditions. Some species succeeded while others gradually disappeared when they could no longer survive in changing environments. Throughout the Triassic, life showed a remarkable ability to recover from one of the greatest biological crises in Earth's history. Every new generation of plants and animals contributed to rebuilding ecosystems that had once been nearly destroyed. Small evolutionary changes accumulated over millions of years, leading to the appearance of entirely new groups of living things. By the later part of the Triassic, Earth supported increasingly rich communities of plants, insects, reptiles, mammals, flying animals, and marine life that continued to develop into the periods that followed. The Great Mass Extinction that happened before the Triassic began was one of the most important events in the long history of Earth. It marked the end of the Permian period and cleared the way for the Triassic period to begin. This event happened about 252 million years ago. It was the largest known mass extinction that Earth has ever experienced. Life on land and in the oceans changed in ways that had never happened before. Many kinds of living things disappeared forever. It was the largest known mass extinction that Earth has ever experienced. Life on land and in the oceans changed in ways that had never happened before. Many kinds of living things disappeared forever, while only a small number survived. Those survivors later became the ancestors of many new forms of life that appeared during the Triassic Period. Before this extinction happened, Earth was already very different from the world that exists today. The continents were joined together into one giant landmass called Pangaea. A huge ocean surrounded this single continent. The climate across much of the land was dry, with many areas receiving very little rain. Some regions had forests, rivers, lakes and wetlands, while others had wide deserts and rocky plains. Different kinds of plants covered parts of the land, including seed ferns, conifers, giant club mosses, horsetails, and many other ancient plants. These plants supported many kinds of animals that lived in forests, open lands, rivers, and swamps. The oceans also held a rich variety of life. Coral reefs stretched across warm, shallow seas. Many fish species swam through the water. Shellfish covered the sea floor. Large predators hunted smaller animals. Strange sea creatures with hard shells, soft bodies, and long arms lived in different parts of the oceans. Tiny, floating organisms formed the base of the food chain. The seas were full of life, and many different ecosystems had developed over millions of years. Life on land was also rich and varied. Large plant-eating animals walked across forests and plains. Meat-eating hunters searched for prey. Small reptiles lived alongside larger animals. Amphibians stayed close to rivers and wetlands. Insects filled the air and crawled across the ground. Every habitat supported many living things that depended on one another for food, shelter, and survival. Scientists believed that this rich world slowly moved toward disaster because of a series of powerful natural events. These events did not happen in a single day. The extinction unfolded over a long period of time. Different regions of Earth were affected in different ways, but eventually the damage spread across nearly the entire planet. One of the main causes that scientists study is a huge period of volcanic activity in an area that is now part of northern Asia. These volcanoes were not like a single mountain erupting for a short time. Instead, enormous amounts of molten rock poured onto the surface again and again over a very long period. Thick layers of lava spread across huge areas of land. Today, these rocks are known as the Siberian Traps. The eruptions released massive amounts of gases into the atmosphere. Among the gases released were carbon dioxide, sulfur dioxide, and other volcanic gases. Carbon dioxide is known for trapping heat in the atmosphere. As more carbon dioxide entered the air, Earth's average temperature began to rise. This warming did not happen instantly, but over many years the climate became hotter and less stable. Sulfur dioxide also had important effects. It could react with water in the atmosphere to produce acid rain. Acid rain damaged forests, polluted rivers and lakes, and affected many plants. Soil became less healthy in some places. Freshwater habitats became harder places for animals to survive. Plants that formed the base of many food chains struggled to grow under these changing conditions. The volcanic eruptions also filled the atmosphere with ash and tiny particles. These particles could block some sunlight for a time. Less sunlight meant that temperatures in some places briefly dropped before rising again as greenhouse gases built up. Plants depended on sunlight to make food. When sunlight decreased, plant growth slowed. Animals that depended on those plants also suffered. The climate became increasingly difficult. for living things. Temperatures rose higher than many plants and animals could tolerate. Some regions became much drier. Rivers shrank, lakes became smaller, wetlands disappeared, forests began to die in some areas. Animals searching for water and food faced growing challenges. As temperatures increased, the oceans also changed. Warm water holds less oxygen than cooler water. Many sea animals depended on oxygen dissolved in the water. As oxygen levels dropped, large areas of the oceans became difficult places to live. Some parts of the sea became almost completely without oxygen. Fish and many other marine animals could no longer survive in these conditions. Scientists describe these low oxygen conditions as ocean anoxia. When oxygen disappeared from the water, many animals living on the seafloor died. Creatures that could not move away were especially affected. Even animals that could swim often struggled because large parts of the oceans no longer provided enough oxygen. Another problem developed when certain kinds of bacteria became more common in low oxygen waters. Some of these bacteria produced poisonous gases, such as hydrogen sulfide. If enough of this gas reached the surface, it could poison marine life. Some scientists think that hydrogen sulfide may even have escaped into the atmosphere in certain places, making conditions worse for plants and animals living on land. The oceans also became more acidic because extra carbon dioxide dissolved into seawater. Ocean acidification made it difficult for many sea creatures to build shells and skeletons made from calcium carbonate. Corals, shellfish, and many tiny organisms depended on this material. As the water became more acidic, these animals struggled to grow and reproduce. Coral reefs suffered greatly during this time. Reefs supported many different species by providing food, shelter, and breeding grounds. When reefs died, countless other animals also lost their homes. Entire marine ecosystems began to break apart. The collapse of food chains spread through both the oceans and the land. Tiny organisms that formed the foundation of the marine food web declined. Animals that fed on them lost an important food source. Larger predators then found fewer prey animals to hunt. The loss continued from one level of the food chain to another until many species disappeared. On land, the loss of forests and other plants affected plant-eating animals first. Without enough food, many herbivores died. Meat-eating animals then struggled because their prey became rare. Small populations became even smaller. Many species could no longer reproduce fast enough to replace those that died. Scientists have found fossil evidence showing that forests disappeared across many regions. Layers of rock from this time often contain signs of dead plant material, burned wood, and sudden changes in pollen and spores. These clues help researchers understand how widespread the destruction became. The extinction affected insects as well. Insects are usually very successful at surviving environmental changes, yet this event caused many insect groups to disappear. This remains one of the few known times when insects experienced a major extinction. Fossil evidence shows changes in insect diversity and in the kinds of damage found on fossil leaves. Many amphibians suffered because they depended on fresh water for breeding and survival. As rivers dried and wetlands disappeared, their habitats became smaller. Higher temperatures also placed extra stress on their bodies. Many amphibian groups became much less common. Large reptiles living before the Triassic also faced severe losses. Some groups vanished completely. Others survived only in small numbers. These survivors later spread into empty habitats after the extinction ended. Many plant species disappeared, although some survived in isolated areas where conditions remained suitable. Plants that could tolerate dry weather or changing temperatures often had a better chance of surviving than those that needed stable conditions. Even so, survival was never guaranteed. Scientists estimate that around 90% of marine species disappeared during this extinction. On land, about 70% of vertebrate species became extinct. Many groups that had existed for millions of years vanished forever. These losses were far greater than those seen during most other extinction events. Fossils from before the extinction show many different kinds of animals living together. Fossils from immediately after the extinction show far fewer species. In many places, rocks that once contained rich collections of fossils suddenly contain only a small number of surviving organisms. This sharp decline provides clear evidence of the scale of the disaster. Recovery did not happen quickly. Even after the main extinction ended, Earth remained a difficult place for life. High temperatures continued in many regions. Ocean oxygen levels stayed low for a long time. Volcanic activity may have continued. Food chains needed time to rebuild. Empty habitats slowly became available for surviving species. Scientists think that repeated environmental changes may have caused several waves of extinction instead of only one single event. Some species disappeared earlier, while others survived for a while before finally becoming extinct. Different areas experienced different levels of damage depending on local conditions. The giant continent of Pangaea may also have made conditions worse. Because such a large amount of land was joined together, many inland regions were far from the cooling influence of the oceans. These areas often experienced hotter summers, colder winters, and less rainfall. As the climate became even more extreme, many animals found it difficult to survive. Strong seasonal weather patterns may have developed across the continent. Long dry periods could have been followed by heavy rains and flooding. Such unstable conditions made it harder for plants to grow and for animals to find reliable sources of food and water. Some scientists have suggested that methane gas also played a role in the extinction. Methane is a powerful greenhouse gas. It may have been released from frozen deposits beneath the ocean floor as temperatures increased. Once released into the atmosphere, methane would have added to global warming and increased environmental stress. Another idea suggests that warming oceans may have allowed certain microorganisms to produce even more greenhouse gases. Although researchers continue to study these possibilities, the exact details remain uncertain. Many scientists believe that several natural processes acted together instead of only one single cause. Scientists study ancient rocks to understand what happened during this period. Layers of volcanic rock reveal when eruptions occurred. Chemical changes preserved inside rocks show shifts in the atmosphere and oceans. Tiny fossils reveal which organisms survived and which disappeared. These pieces of evidence help build a picture of the changing world. Scientists also examine fossil pollen and spores. Different plants produce different pollen shapes. By studying these tiny fossils, researchers can tell which plants were common before the extinction and which plants appeared afterward. This helps reveal how forests and other plant communities changed through time. Carbon found inside ancient rocks also provides important clues. Changes in carbon levels show that Earth's carbon cycle experienced major disturbances during this period. These changes support the idea that enormous amounts of carbon entered the atmosphere through volcanic activity and other natural processes. Scientists measure oxygen levels preserved in minerals and fossils. These measurements help estimate ancient temperatures. Many studies suggest that Earth became much warmer during the extinction event. Some tropical sea temperatures may have become too high for many marine animals to survive. The extinction also changed the kinds of animals that dominated Earth afterward. Before the event, many successful animal groups ruled the land and seas. After the extinction, many of those groups had disappeared. The surviving species entered habitats that were now almost empty. One important group that survived included early relatives of crocodiles and dinosaurs. At first, they were small and not especially common. During the Triassic period, they slowly spread into many different environments. Over time, they evolved into many new forms. The ancestors of mammals also survived, although their numbers became much smaller. These early relatives were generally small animals. Their survival allowed mammals to continue evolving through later periods of Earth's history. Many marine animals that survived also gave rise to new groups. New coral communities slowly developed. Fish populations gradually increased again. Shellfish returned to many coastal waters. Recovery happened over millions of years, rather than in a short time. Plants also slowly returned. Ferns often became some of the first plants to spread into damaged landscapes. They could grow quickly in disturbed ground. As conditions slowly improved, forests gradually expanded once more. Different plant communities appeared in different regions depending on local climate and soil conditions. The extinction affected Earth's ecosystems in ways that lasted for millions of years. The disappearance of so many species meant that many ecological roles became empty. Surviving animals and plants slowly filled these roles through evolution. New species appeared while older groups remained extinct forever. Scientists continue to debate the exact sequence of events. New fossils are discovered every year. Improved laboratory methods allow researchers to study tiny chemical signals inside ancient rocks with greater accuracy. Each new discovery adds another piece to the story of this remarkable event. Some researchers investigate volcanic rocks to determine how long the eruptions lasted. Others examine ocean sediments to understand changes in sea chemistry. Still others study fossil bones, shells, teeth, pollen, and spores. Together, these different fields provide a fuller understanding of the extinction. The rocks formed during this time are found on several continents. Scientists working in Asia, Europe, Africa, North America, South America, Australia, and Antarctica have discovered evidence that supports the worldwide nature of the extinction. Similar changes appear in many different regions, showing that the event affected nearly the entire planet. Some animals survived because they were able to eat many different kinds of food. Others survived because they lived in environments that changed less than surrounding areas. Small body size may also have helped some species because they required less food. Even with these possible advantages, survival remained extremely difficult. Many surviving animals likely faced long periods with limited food supplies. Reproduction may have slowed because adults were weak or because young animals struggled to survive. Populations remained small for many generations before beginning to recover. The extinction also influenced the pace of evolution. With many habitats left empty, surviving species encountered new opportunities. Over millions of years, they adapted to changing environments and gradually produced new species. This process eventually led to the appearance of many important animal groups that became common during the Triassic period. Scientists have discovered fossil footprints from the early Triassic that show animals moving across landscapes recovering from the extinction. These footprints reveal which animals were present, even when complete skeletons have not been found. They also show how animals traveled across riverbanks, floodplains, and muddy ground. Ancient river deposits reveal changing patterns of rainfall. Some river channels became wider because heavy storms occasionally produced powerful floods. At other times, rivers nearly disappeared. because dry conditions lasted for long periods. These changing environments affected where plants and animals could live. Evidence from fossil soils also shows changing climates. Some ancient soils formed under wet conditions, while others developed in dry environments. Layers of minerals preserved inside these soils help scientists understand rainfall, temperature, and seasonal weather patterns. The extinction reached nearly every type of environment. Deep oceans, shallow seas, rivers, lakes, forests, deserts, wetlands, mountains and coastal regions all experienced major changes. Few places escaped completely from the environmental stress spreading across Earth. Many fossils from after the extinction belong to only a few hardy species. These organisms often spread across large areas because there were fewer competitors. Scientists sometimes describe these species as disaster forms because they became common soon after the extinction, while ecosystems slowly recovered. Over time, diversity slowly increased again. New species evolved, populations expanded, and ecosystems became more complex. The first part of the Triassic period remained a challenging time, but life gradually rebuilt itself through natural processes that continued over millions of years. The great mass extinction before the Triassic period remains one of the most carefully studied events in Earth science, because it changed the direction of life's history. It removed countless species that had dominated Earth for millions of years and left only a fraction of living organisms to continue into the next chapter of Earth's history. The survivors faced a harsh world filled with heat, unstable climates, damaged ecosystems, shrinking forests, changing rivers, oxygen-poor oceans, acidic seas, limited food, and widespread environmental stress. From these surviving plants, animals, fungi, and microorganisms, life slowly continued into the Triassic period, where new ecosystems gradually formed and new groups of living things began to spread across the recovering planet. About 252 million years ago, Earth entered the Triassic period after the greatest mass extinction known in the history of life. During this time, almost all of the world's land was joined together into one enormous supercontinent called Pangaea. This giant landmass played a major part in shaping the world of the Triassic. It affected the weather, the climate, rivers, deserts, plants, animals, and the early evolution of dinosaurs and many other living things. The shape and size of Pangaea changed the way Earth looked and worked in ways that influenced almost every part of life during the Triassic period. Pangaea had formed before the Triassic began. Over millions of years, smaller continents slowly moved across Earth's surface until they joined together into one huge landmass. This process happened because the outer layer of Earth is broken into large pieces called tectonic plates. These plates move very slowly across the surface. Even though the movement is usually only a few centimeters each year, it continues for millions of years. Over a very long time, continents can travel great distances, come together, and later separate again. By the beginning of the Triassic period, nearly all of Earth's land was connected. Pangaea stretched from areas close to the North Pole all the way toward areas close to the South Pole. It covered a huge part of the planet. Around it was one enormous ocean called Pangaea. Along the eastern side of Pangaea was a smaller sea called the Tethys Ocean. This arrangement gave the Earth a very different appearance from today. Instead of many separate continents divided by wide oceans, there was one massive landmass surrounded by a giant body of water. The size of Pangaea had a powerful effect on the climate. Large oceans help carry moisture into nearby land, bringing rain and helping keep temperatures more even. Since Pangaea was so large, Much of its interior was very far from the sea. Moist ocean air could not easily reach these central regions. As a result, large parts of the interior became very dry. Rain fell much less often than in coastal areas, and vast deserts formed across many regions. These deserts were among the largest that had ever existed. Sand dunes stretched across great distances. Strong winds moved loose sand from place to place. Dry riverbeds were common. Some rivers only flowed during short, rainy seasons before drying up again. Lakes often became smaller or disappeared completely during long dry periods. Water became one of the most important resources for both plants and animals living in these inland regions. The climate across Pangaea was not the same everywhere. Areas near the coasts usually received more rain because they were closer to the ocean. Rivers flowing from wetter regions sometimes carried water into drier places. Coastal forests could survive more easily than forests deep inside the continent. The Tethys Ocean also provided moisture to nearby lands, allowing different kinds of plants and animals to live there. The middle of Pangaea experienced very hot summers. Without nearby oceans to soften temperatures, the land heated quickly under the sun. During winter, temperatures could become much cooler. This created strong seasonal changes in many places. Animals had to survive both extreme heat and cooler periods during the year. Plants also had to adapt to changing temperatures and long dry seasons. Scientists study ancient rocks to learn about the climate of the Triassic period. Layers of sandstone found in many parts of the world show that large deserts once covered these regions. Ripple marks left by ancient rivers, dried mud cracks and preserved sand dunes provide evidence of dry conditions. Fossils of plants and animals also help scientists understand where wetter forests and rivers once existed. Rainfall across Pangaea often followed seasonal patterns. Some regions received heavy rains for a short time before long dry months returned. During rainy seasons, rivers filled with water, lakes expanded, and plants grew quickly. Animals gathered around fresh water to drink, feed, and reproduce. During dry seasons, many rivers shrank or disappeared. Plants stopped growing as quickly, and animals searched for reliable sources of water. Some animals likely traveled long distances in search of food and water. Fossil evidence suggests that certain reptiles moved across wide areas. The large connected landmass made long journeys possible without crossing oceans. Animals could spread into new regions more easily because there were no wide seas separating most land areas. Plants living in the Triassic had to deal with difficult conditions across much of Pangaea. Many forests that had existed before the Great Extinction disappeared. New plant communities slowly developed as life recovered. Tough plants that could survive dry weather became common in many places. Seed-producing plants became especially important because seeds could survive periods without water better than many earlier forms of reproduction. Conifers became some of the most successful trees during the Triassic. These trees produced seeds inside cones. Their narrow leaves helped reduce water loss. Many species could survive in areas where rainfall was limited. Conifer forests spread across regions that received enough moisture while also surviving seasonal dry periods. Cycads also became common during the Triassic. These plants had thick trunks and crowns of large leaves. Although they looked somewhat like palm trees, they belonged to a different group of plants. Their strong structure helped many species survive difficult climates. Cycads grew in many warm parts of Pangaea. Another important group of plants included ginkgo relatives. These trees had fan-shaped leaves and reproduced using seeds. Some ancient members of this group lived across different parts of Pangaea. Today, only one living species remains. providing scientists with a small connection to this ancient plant family. Ferns also survived the Great Extinction and continued growing during the Triassic. They often thrived near rivers, lakes, and wetter regions where enough water remained available. Ferns reproduced using spores instead of seeds. Although they depended more heavily on moisture, they continued to play an important role in many ecosystems. The recovery of plant life was slow after the Great Extinction. Large areas may have remained sparsely covered for long periods. As climates became more stable in some regions, forests slowly expanded. Plants helped hold soil in place, reduced erosion, and created habitats for insects and animals. Their leaves, seeds, and stems provided food for many plant-eating creatures. The connected landmass of Pangaea allowed many kinds of plants to spread across enormous distances. Since there were few large ocean barriers, seeds could slowly move into new regions through wind, rivers, and animal activity. Over many generations, plant groups became established across wide areas of the supercontinent. Animals also benefited from the connected land. Many reptiles expanded their range into different environments. Early relatives of crocodiles, turtles, lizards, mammals, and dinosaurs all lived during the Triassic. Some groups spread across thousands of kilometers over millions of years because they could move through connected habitats without needing to cross oceans. The earliest dinosaurs appeared during the later part of the Triassic period. At first, they were usually smaller than many other reptiles living at the time. Their success was influenced partly by the geography of Pangaea. Since the continents were joined together, early dinosaurs gradually spread into many different regions. Fossils of closely related dinosaurs have been found on continents that are now separated by vast oceans. These discoveries make sense because those continents were once connected as part of Pangaea. The ancestors of mammals also lived during the Triassic. These early mammal relatives were generally small. Many were active at night, where cooler temperatures may have helped them avoid daytime heat. They fed on insects, small animals, seeds, and plants depending on the species. Their small size helped them hide from larger predators. Large amphibians survived in wetter environments. Many stayed close to rivers, lakes, and swamps because they depended on water for reproduction and survival. Dry inland deserts limited where these animals could live. Their fossils are usually found in places that once contained freshwater habitats. Insects remained an important part of Triassic ecosystems. They pollinated some plants, broke down dead material, and served as food for many animals. Beetles, dragonflies, and other insect groups survived the Great Extinction and continued evolving during the Triassic. Their success supported many food chains across Pangaea. The giant supercontinent also influenced the movement of rivers. Rivers flowing across broad, flat landscapes sometimes changed direction over long periods. Seasonal flooding shaped valleys and carried sediments across large areas. These sediments later became rock layers that scientists study today. Ancient river deposits provide important information about rainfall, climate, and the animals that once lived nearby. Mountain ranges within Pangaea also affected local climates. As moist air moved toward mountains, rainfall often increased on one side, while the opposite side became drier. These regional differences created a variety of habitats, despite the overall dry conditions across much of the supercontinent. Earth during the Triassic generally had higher levels of carbon dioxide in the atmosphere than today. This helped create warm global temperatures. The absence of large permanent ice sheets meant that sea levels and weather patterns differed from those of later periods. Warm conditions reached many parts of the planet, although temperatures still varied with latitude and elevation. The coastline of Pangaea stretched for enormous distances. coastal environments supported many different forms of life. Rivers carried nutrients into shallow seas, helping marine ecosystems grow. Beaches, lagoons, estuaries and coastal plains created habitats where plants and animals could thrive. Marine reptiles became important animals in the oceans surrounding Pangaea. Ichthyosaurs developed bodies well suited for swimming and hunted fish and squid. Nothosaurs lived in coastal waters and likely hunted smaller marine animals. Later in the Triassic, plesiosaur relatives also appeared. Although these reptiles lived in water, they still breathed air and returned to the surface regularly. The Panthalassa Ocean covered most of Earth's surface. Because it was so large, it influenced global weather patterns. Ocean currents carried heat around the planet, although scientists continue studying exactly how these currents moved during the Triassic. The interactions between the ocean and the atmosphere helped shape rainfall and temperatures across different parts of Pangaea. The Tethys Ocean was especially important because it lay between northern and southern parts of the supercontinent. Warm, shallow waters supported many marine organisms, including corals, shellfish, fish, and reptiles. Coastal regions near the Tethys often had greater plant diversity because more moisture reached nearby land. Coral reefs slowly recovered after the Great Extinction. Reef-building organisms faced severe losses during the extinction event, but new reef communities gradually developed during the Triassic. These reefs became homes for many marine animals and supported growing ocean ecosystems. Fish populations also recovered. Ray-finned fishes expanded into many habitats. Sharks survived the extinction and continued evolving throughout the Triassic. Marine food chains slowly became more complex as ecosystems recovered over millions of years. The connected continents allowed diseases, parasites, and competing species to spread more easily than if land had been divided into separate continents. Animal populations interacted across large regions. This increased opportunities for evolution as species adapted to different climates, predators, and food sources. Volcanic activity also influenced life during parts of the Triassic. Earth remained geologically active. Volcanoes released lava, ash, and gases into the atmosphere. These eruptions sometimes changed local environments. New rock formed from cooling lava, while volcanic ash enriched some soils with minerals that later supported plant growth. Earthquakes occurred as tectonic plates continued moving beneath Pangaea. Although these events happened over millions of years, they gradually changed landscapes. Rivers shifted, mountains rose, and valleys formed. These slow geological processes continuously reshaped habitats across the supercontinent. Toward the later part of the Triassic, the first signs of Pangaea beginning to break apart appeared. Cracks slowly formed within the continent as tectonic forces pulled different regions apart. At first, these changes happened extremely slowly. People living today would never notice such movement during a lifetime. But over millions of years, the changes became enormous. As the crust stretched, long valleys formed in some regions. Volcanoes often developed along these weakening areas. Magma rose toward the surface, creating new volcanic rocks. Eventually, some valleys widened enough for seawater to enter, beginning the formation of new oceans. The early stages of Pangaea's breakup started changing regional climates. New coastlines slowly developed. Moisture could reach inland areas more easily in some places. Rainfall patterns gradually shifted. Plants and animals responded by spreading into newly suitable habitats while disappearing from others. During most of the Triassic, however, Pangaea remained largely connected. This continued to allow animal populations to move widely across the land. Many fossil species have been discovered on continents that today lie thousands of kilometers apart. Fossils of similar reptiles, early dinosaurs, amphibians and plants found in South America, Africa, North America, Europe, Asia, Antarctica and Australia provide strong evidence that these lands were once joined together. Scientists did not always know that Pangaea had existed. During the early part of the 20th century, researchers noticed that coastlines on opposite sides of the Atlantic Ocean appeared to fit together. They also found matching fossils, rock layers, and mountain belts on continents now separated by oceans. These discoveries eventually helped support the idea of continental drift, which later became part of the modern theory of plate tectonics. The rocks formed during the Triassic preserve many clues about life on Pangaea. Fossils are found in river deposits, lake sediments, desert sandstones, volcanic rocks, and coastal formations. Scientists carefully study these rocks to understand ancient climates, rainfall, vegetation, and animal communities. Footprints preserved in mud provide valuable information about Triassic animals. Sometimes footprints reveal the presence of species even when bones are not found. Trackways show how animals walked, how fast they moved, and whether groups traveled together. Some footprints belong to early dinosaurs, while others were left by crocodile relatives, amphibians, and different reptiles. Plant fossils also reveal changing climates across Pangaea. Leaves, wood, pollen, seeds, and spores help scientists identify ancient forests and seasonal changes. Growth rings preserved in fossil wood sometimes show periods of faster and slower growth, providing clues about yearly weather conditions. Sedimentary rocks formed by rivers and lakes contain minerals that indicate ancient climates. Mudstones, sandstones, and limestone each preserve different environmental information. Scientists combine evidence from many rock layers to build detailed pictures of Triassic landscapes. The dry climate influenced soil development across much of Pangaea. In arid regions, evaporation often left minerals behind in the ground. Some ancient lake beds contain thick mineral deposits that formed as water slowly disappeared. These deposits help scientists identify regions that experienced repeated cycles of flooding and drying. Wind played a major role in shaping landscapes across the deserts of Pangaea. Sand grains blown across the ground gradually built towering dunes. These dunes shifted over time as winds changed direction. Today, ancient dunes preserved in rock still show the direction of prevailing winds during the Triassic. Wildfires probably occurred during dry seasons in forested regions. Lightning could ignite dry vegetation, especially after long periods without rain. Fires removed old plant growth and opened space for new plants. Some fossil charcoal found in Triassic rocks provides evidence that fires were part of ancient ecosystems. The atmosphere of the Triassic supported flying insects, although no birds yet existed during most of the period. The first true birds would not appear until much later. Flying reptiles called pterosaurs evolved during the Triassic and became the first vertebrates to achieve powered flight. They spread across many regions of Pangaea and hunted insects, fish, and small animals depending on the species. Pangaea also influenced animal evolution by creating isolated habitats within the same continent. Mountain ranges, deserts, rivers, and climate differences separated populations even though no oceans divided them. Over long periods, isolated groups developed new features that helped them survive local conditions. Large desert regions acted as natural barriers. Some animals could not cross these harsh environments because food and water were too limited. As a result, populations living on opposite sides of major deserts sometimes evolved separately. This helped increase biological diversity across the supercontinent. Seasonal rivers created temporary habitats. During wet months, fish and amphibians spread through connected waterways. During dry months, isolated pools trapped aquatic animals until rains returned. Some species developed ways to survive these changing conditions. Egg-laying animals benefited from adaptations that reduced dependence on water. Reptile eggs contain protective coverings that allowed embryos to develop on land. This gave reptiles an advantage in many dry regions where amphibians struggled. Dinosaurs, crocodile relatives, turtles, and many other reptiles reproduced successfully across much of Pangaea because they were less dependent on standing water. Many animals developed strong legs suited for walking long distances across dry landscapes. Some predators followed migrating plant eaters between feeding areas. Others remained close to rivers where prey gathered during dry seasons. The movement of animals across Pangaea helped spread species into new environments over many generations. Life during the Triassic was still recovering from the greatest extinction Earth had experienced. Entire ecosystems had disappeared before the Triassic began. New communities slowly formed as surviving species adapted to changing conditions. Pangaea provided both challenges and opportunities during this recovery. Harsh climates limited some forms of life, while connected land allowed surviving groups to expand into empty habitats. Early dinosaurs were only one part of the changing world. Many other reptiles dominated different environments. Crocodile relatives occupied rivers and floodplains. Marine reptiles ruled many ocean habitats. Pterosaurs took to the skies. Mammal ancestors remained small but continued evolving. Each group found ways to survive within the landscapes shaped by the supercontinent. As millions of years passed, tectonic forces beneath Earth's surface continued pulling Pangaea apart. Although the changes were extremely slow, they eventually transformed the world. New oceans formed, coastlines increased, climates became more varied, and animal populations became separated. These later changes influenced the evolution of dinosaurs, mammals, flowering plants, and many other groups that would dominate future periods of Earth's history. The story of the Triassic cannot be understood without recognizing the enormous influence of Pangaea. Its immense size controlled rainfall, temperatures, deserts, rivers, forests, coastlines, and migration routes. It determined where plants could grow, where animals could find water, and how species spread across the world. Every major environment of the Triassic was connected in some way to the existence of this vast supercontinent, and its slow movement continued shaping Earth's surface throughout the entire period. The Triassic period was the first period of the Mesozoic era. It began after the largest known mass extinction in Earth's history. During this time, life on land and in the oceans slowly recovered from the enormous losses that had happened at the end of the Permian period. The world of the Triassic was very different from the world people know today. The climate, the seasons, the shape of the land, and the appearance of the environment all played important roles in the lives of plants and animals. Every living thing had to survive under conditions that were often hot, dry, and difficult. One of the biggest reasons for the unique climate of the Triassic was the arrangement of Earth's land. Most of the continents were joined together into one huge landmass called Pangaea. Since almost all of the land was connected, there were very few large inland seas. The oceans surrounded this giant landmass, but the center of Pangaea was very far from the cooling influence of the sea. This had a strong effect on temperatures, rainfall, and the changing seasons across the planet. The middle regions of Pangaea were often dry because moist air from the oceans could not easily travel far into the interior of the continent. As clouds moved inland, much of their moisture had already fallen as rain closer to the coasts. By the time they reached the center of the continent, there was very little water left. This created wide, dry areas where rainfall was rare for long periods. The climate across much of the Triassic world was warmer than today. There were no permanent ice sheets covering the poles like those found during some other periods of Earth's history. Without large ice sheets, the planet stayed warm from the equator towards the poles. Temperatures could still vary from place to place, but the overall world was generally warm. The atmosphere during the Triassic also differed from the atmosphere of today. Levels of carbon dioxide were much higher than modern levels. Carbon dioxide traps heat in the atmosphere. Higher amounts helped keep Earth warmer. Volcanoes released large amounts of gases into the air over long periods. These volcanic gases added carbon dioxide and other substances that affected the climate. Many scientists believe that volcanic activity remained important throughout much of the Triassic. Volcanoes were found in different regions of the world as the crust slowly changed. Although the greatest volcanic events connected with the breakup of Pangaea happened near the end of the Triassic, volcanic activity had already been shaping the environment for millions of years before that time. The hot climate affected nearly every part of daily life for Triassic plants and animals. Water became one of the most valuable natural resources in many regions. Rivers, lakes, and wetlands often became centers of life because they offered fresh water and supported many kinds of plants. Animals gathered around these places to drink, hunt, hide, or reproduce. The dry climate did not mean that every part of the world was a desert. Different regions had different weather patterns. Coastal areas often received more rain because they were close to the oceans. Mountain regions could also receive more rainfall when moist air rose over higher ground and cooled. River valleys supported forests and rich plant life even when nearby areas remained dry. Large deserts covered many parts of the interior of Pangaea. Wind shaped the sand into large dunes that stretched across the landscape. These deserts experienced very hot daytime temperatures. At night, temperatures often dropped because dry air does not hold heat as well as moist air. Animals living in these areas had to deal with both daytime heat and cooler nights. Evidence for these ancient deserts comes from rocks that formed during the Triassic. Thick layers of sandstone preserve the shapes of old sand dunes. The patterns found in these rocks show the direction of ancient winds and reveal how sand moved across the land over long periods. Rainfall during the Triassic was often seasonal rather than evenly spread throughout the year. Some places experienced long dry seasons followed by periods of heavy rain. Rivers that were dry for much of the year could suddenly fill with fast-moving water after powerful storms. Floods sometimes spread across low areas before the water slowly disappeared again. Seasonal rainfall created cycles that affected every living thing. Plants often grew rapidly after rain arrived. Seeds sprouted, leaves appeared, and new growth covered the ground. Animals took advantage of these changes by feeding, reproducing, and raising their young when food and water became more available. When the dry season returned, many streams became smaller or disappeared completely. Some lakes shrank as water evaporated under the hot sun. Plants that could not survive the lack of moisture died back or entered resting stages until rain returned. Animals searched for remaining water sources or developed ways to survive long dry periods. Many Triassic rivers behaved differently from many rivers today. Some flowed throughout the year, especially those fed by mountains or regions with more rainfall. Others were temporary rivers that carried water only during wet seasons. Their channels remained dry for much of the year until storms filled them once again. Floodplains formed beside many rivers. These flat areas received fresh layers of mud and sand whenever rivers overflowed. Floodplains often supported dense plant growth because the soil contained water and nutrients. Many animals spent much of their lives in these productive environments. Lakes varied greatly in size and depth. Some remained full for long periods, while others expanded during rainy seasons and became much smaller during dry seasons. As water levels changed, shorelines moved back and forth across the landscape. Fish, amphibians, reptiles, insects, and many other living things depended on these freshwater habitats. Wetlands also existed in parts of the Triassic world. Marshes, swamps, and shallow pools supported rich communities of plants and animals. Ferns, horsetails, and other moisture-loving plants grew in these areas. Small animals found shelter among the thick vegetation, while larger predators searched for prey nearby. The coastlines of the Triassic look different from modern coastlines because the continents were joined together. Long coastal plains bordered much of Pangaea. Beaches, mudflats, lagoons and shallow seas created many different habitats where marine and land environments met. Shallow seas supported many kinds of marine life. Coral reefs slowly recovered after the great extinction that came before the Triassic. New reef-building organisms spread through warm, shallow waters. Fish, shellfish, marine reptiles, and many smaller creatures lived among these underwater environments. The oceans themselves experienced changes during the Triassic. Ocean temperatures were generally warm. Warm water influenced weather patterns around the globe. Ocean currents transported heat from one region to another, although the arrangement of the continents made these currents different from those seen today. Scientists believe that some parts of the oceans had lower oxygen levels than modern oceans. Low oxygen conditions made survival difficult for certain marine animals, while allowing others to become successful. Ocean chemistry slowly changed as marine ecosystems recovered from the earlier mass extinction. Storms were an important part of the Triassic climate. Powerful seasonal storms brought heavy rainfall to many regions. Strong winds moved large amounts of sand across deserts and carried dust over long distances. Storms also caused flooding that reshaped river valleys and deposited fresh sediments. Lightning from storms sometimes started wildfires in dry forests and grass-covered areas. Evidence from fossil charcoal suggests that fires occurred naturally during parts of the Triassic. Fire affected plant communities by clearing older vegetation and allowing new growth to appear after rainfall returned. The seasons during the Triassic were often very strong because of the huge size of Pangaea. Large land areas heat up and cool down faster than oceans. During warmer months, the land became extremely hot. During cooler months, temperatures dropped more noticeably than they did near the coast. Many scientists think that parts of the Triassic experienced seasonal wind systems similar in some ways to modern monsoon climates. During certain parts of the year, winds brought moist air from the oceans onto land, leading to periods of heavy rainfall. During other parts of the year, winds changed direction, bringing dry conditions instead. These seasonal wind changes helped shape the yearly lives of plants and animals. Reproduction often happened during wetter times when food was more plentiful. Young animals had better chances of survival when water and vegetation were available in larger amounts. Plants developed different ways to survive changing seasons. Some plants produced thick leaves that reduced water loss. Others developed deep roots that reached underground moisture. Certain plants dropped their leaves during dry periods to conserve water until better conditions returned. Seed-producing plants became especially important during the Triassic. Seeds could survive dry conditions much better than many earlier methods of reproduction. They protected young plant embryos until enough moisture became available for growth. Conifers spread across many regions during the Triassic. These trees often had narrow leaves that helped reduce water loss. They formed forests in areas where rainfall was sufficient. Their seeds provided food for many plant-eating animals. Cycads were also common during the Triassic. These seed plants had thick trunks and crowns of stiff leaves. Many grew well in warm climates and became familiar parts of Triassic landscapes. Their appearance remained successful for millions of years afterward. Ginkgo relatives also lived during this time. Some of these plants grew in regions with seasonal climates. Their leaves collected sunlight during favorable parts of the year before falling during less suitable seasons. Ferns remained abundant, especially in wetter regions. They covered the ground beneath forests and spread across riverbanks and wetlands. Fern spores required moisture for successful reproduction, making these plants more common in places where water remained available. Horsetails grew near streams and marshes. Their hollow stems rose above wet ground, where they formed dense stands. These plants reproduced using spores and thrived in moist environments. The landscapes of the Triassic included mountains formed during earlier geological events. These mountains influenced rainfall by forcing moist air upward. As the air cooled, rain fell on one side of the mountains while the opposite side often remained much drier. Rocky hills, open plains, forests, deserts, rivers, lakes, wetlands and coastlines all existed across the vast landmass. Each environment supported different groups of living things depending on the amount of water, temperature and available food. Some regions had red-coloured soils formed under warm conditions with seasonal rainfall. These red rocks remain important evidence for scientists studying Triassic climates. Minerals within the rocks changed as they reacted with oxygen in warm environments. Wind constantly shaped dry landscapes. Sand dunes slowly moved across deserts. Fine dust travelled great distances before settling. Layers of dust sometimes became buried and later turned into rock, preserving records of ancient climates. Water also shaped the land through erosion. Rivers carried sand, gravel and mud from higher ground to lower areas. Floods spread these materials across floodplains. Over long periods, thick layers of sediment built up, later becoming sedimentary rocks that preserve fossils today. The changing climate influenced the distribution of animals across Pangaea. Some species preferred wetter forests and river valleys. Others adapted to dry plains or desert margins. Their fossil remains help scientists understand where different climates existed. Early dinosaurs first appeared during the Triassic. At first, they were small members of the animal communities. Many lived in regions where seasonal rainfall supported enough plant life and prey animals. Their success depended partly on adapting to changing environmental conditions. Large amphibians often stayed close to rivers and lakes because their lives depended heavily on water. Dry regions limited where they could survive. During wet seasons, they expanded into temporary pools and flooded areas before returning to permanent water sources as dry weather returned. Many reptiles were better suited to dry climates. Their skin reduced water loss, and many reproduced through eggs protected by shells. These features allowed reptiles to spread into environments where amphibians faced greater difficulties. Insects were widespread across Triassic landscapes. They pollinated certain plants, fed on leaves, recycled dead material, and served as food for many larger animals. Seasonal changes affected insect populations as rain encouraged new plant growth. The skies of the Triassic were often clear over desert regions. Dry air allowed strong sunlight to reach the ground. Clouds became more common during rainy seasons and along coasts where moisture was greater. Sunlight warmed the land quickly during the day. Rocks and sand absorbed heat. After sunset, temperatures dropped because little moisture remained in the air to hold warmth. Animals active at night benefited from these cooler conditions. Many animals likely adjusted their daily activities to avoid the hottest parts of the day. Some searched for food during early morning or evening hours. Others rested in shade, burrows, or near water until temperatures became less severe. Burrowing became an effective survival strategy for many small animals. Underground shelters stayed cooler during hot days and provided protection from dry winds. Fossil burrows found in Triassic rocks show that this behavior was already common. The smell of wet soil after seasonal rains would have spread across many landscapes as dry ground absorbed water. Plants quickly responded by producing fresh leaves and shoots. Streams that had remained empty for months suddenly carried flowing water. Temporary ponds formed after heavy rain. These pools supported short periods of intense activity as insects reproduced, amphibians laid eggs, and animals gathered to drink. As dry weather returned, many of these ponds slowly disappeared. Dust storms sometimes swept across dry regions. Strong winds lifted loose soil high into the atmosphere. Dust reduced visibility and settled over plants and water sources. Repeated dust storms shaped both the land and the lives of animals. The edges of deserts often supported scattered vegetation rather than completely bare ground. Hardy shrubs, seed plants, and drought-resistant species survived where enough underground moisture remained. These areas provided food for plant-eating animals moving between wetter and drier regions. Salt lakes formed in some dry basins where water entered but had no outlet to the sea. As water evaporated under the hot climate, dissolved minerals remained behind. Thick deposits of salt and other minerals accumulated over long periods. Evaporation played a major role in shaping Triassic environments. Warm temperatures caused water to leave lakes, rivers, and soil rapidly. Areas receiving little rainfall often became even drier, because evaporation exceeded the amount of incoming water. Cloud formation depended heavily on available moisture. Coastal regions produced more clouds because ocean water continuously evaporated into the atmosphere. Inland deserts often remained cloudless for long periods. The poles during the Triassic were much warmer than today, although seasonal changes still occurred because of Earth's movement around the Sun. Permanent ice sheets were absent. Forests and other vegetation extended much farther toward polar regions than they do today. Even in these warmer polar areas, daylight changed throughout the year. Long summer days provided extended periods for plant growth. During winter, daylight became much shorter, influencing the activities of animals and plants. The equatorial regions remained warm throughout the year. Rainfall varied depending on seasonal wind patterns. Some equatorial areas received enough rain to support forests, while others remained dry because of local geography and atmospheric circulation. Ocean shores experienced regular tides that reshaped beaches and mudflats. Marine animals adapted to changing water levels. Coastal plants tolerated salty conditions and shifting sediments. Many fossil footprints preserved in Triassic rocks were formed in soft mud beside rivers, lakes, and coastlines. Later floods buried these tracks beneath fresh layers of sediment. Millions of years afterward, these preserved footprints provide valuable evidence of ancient environments and animal behavior. Tree rings from fossil wood sometimes preserve information about seasonal growth. Wider rings often indicate years with better growing conditions, while narrower rings suggest drier, or less favorable years. These records help scientists reconstruct ancient climate patterns. Chemical information stored inside rocks also provides clues about Triassic temperatures and rainfall. Scientists study the minerals and chemical elements preserved in ancient sediments to estimate environmental conditions from millions of years ago. Pollen grains and spores preserved in rock layers reveal which plants lived in different regions. Because different plants require different amounts of water and warmth, fossil pollen helps reconstruct changing climates across the Triassic world. Some Triassic regions experienced repeated cycles of wetter and drier conditions, lasting many thousands of years. These long-term climate shifts affected the spread of forests, deserts, rivers, and animal populations. The slow movement of Earth's tectonic plates also influenced climate. As the continents gradually shifted, coastlines changed position. Mountains rose or wore away through erosion. Ocean circulation slowly changed as the shapes of land and sea evolved. Near the end of the Triassic, the giant continent of Pangaea began showing clearer signs of breaking apart. Cracks developed in Earth's crust. Volcanic activity increased in many regions. Although the complete separation of the continents would happen later, these early changes already started influencing local climates. Fresh volcanic rock created new landscapes. Lava covered older ground in some places. Ash settled across nearby regions. Over time, weathering broke volcanic rocks into soil that supported new plant growth. The interaction between climate and landscapes remained constant throughout the Triassic. Heat influenced evaporation. Rain shaped rivers. Rivers carved valleys and carried sediment. Wind moved sand across deserts. Plants stabilized soil where moisture allowed them to grow. Animals followed water, food, and shelter as the seasons changed. Every region of the Triassic had its own combination of temperature, rainfall, landforms, and living communities. Some places remained dry for most of the year, others experienced regular seasonal rains. Forests occupied wetter environments, while deserts spread across broad inland areas. Mountains, rivers, lakes, wetlands, coastal plains, and shallow seas created many different habitats where life slowly expanded after the earlier mass extinction. The climate continued changing over millions of years within the Triassic itself. Conditions were not identical from the beginning to the end of the period. Local environments shifted as volcanic activity, continental movement, atmospheric changes, and natural climate cycles influenced temperatures and rainfall. Living organisms responded by spreading into new areas, adapting to seasonal conditions, and developing new ways to survive within the warm and varied landscapes of the Triassic world. The first forests, plants, and ecosystems that appeared after the Great Extinction marked the beginning of a very important stage in the history of Earth. Life had survived one of the most severe extinction events ever known. A very large number of animals and plants had disappeared, and many places that had once supported rich and active ecosystems became empty or greatly damaged. The land looked very different from the way it had looked before the extinction. Many plant groups that had been common became rare, while others disappeared completely from many regions. The forests that had once covered large areas were broken apart, and many places were left with only scattered plants growing across dry ground. Rivers, lakes, floodplains, hills, in coastal areas all showed signs of major environmental change. The recovery of plant life did not happen quickly. It took a very long time before large forests returned and healthy ecosystems became established again. The Great Extinction happened at the end of the Permian period, about 252 million years ago. it removed most living species from the land and the oceans. Scientists believe that massive volcanic activity released huge amounts of gases into the atmosphere. These gases changed the climate, raised temperatures, reduced oxygen in many environments, and disturbed rainfall patterns. Acid rain may have damaged plants and soils. Wildfires probably spread through many forests during this time because hot and dry conditions became common in many regions. Rivers changed their paths, lakes dried up in some places, and soils became weak because plant roots were no longer holding the ground together. Before the extinction, large forests covered many parts of the world. These forests contained different kinds of seed ferns, giant club mosses, horsetails, ferns, and early conifers. They provided food and shelter for insects, reptiles, amphibians, and many other forms of life. Their roots helped protect the soil from erosion, and their fallen leaves helped create rich layers of organic material that supported countless small organisms. After the extinction, many of these forests disappeared over wide areas. Large empty landscapes replaced thick woodlands that had existed for millions of years. When forests disappeared, the effects reached far beyond the loss of trees. The soil became loose because roots were no longer keeping it in place. Heavy rain washed large amounts of dirt into rivers. Streams became filled with mud and sand. Flooding became more common in some places because fewer plants slowed the movement of water. Wind also carried loose soil across dry landscapes. Many rivers deposited thick layers of sediment because they received more material than before. Scientists find these rock layers today and use them to understand the environmental conditions that existed after the extinction. The earliest stages of recovery were dominated by simple plant communities. Small plants that could grow quickly often appeared before larger trees returned. Many of these early plants were able to spread their spores or seeds over long distances. Open ground allowed sunlight to reach the surface, making it easier for these pioneer plants to establish themselves. They helped begin the slow process of rebuilding damaged ecosystems. Ferns became especially important during this period. Scientists have discovered evidence of what is often called a fern spike in rocks from the earliest Triassic period. This means that fossil spores from ferns became extremely common in many locations soon after the extinction. Ferns are often among the first plants to grow after natural disasters because they can spread rapidly into open ground. Their ability to reproduce through spores allowed them to reach damaged areas where larger plants had disappeared. Thick growths of ferns covered many landscapes before forests became established again. These early fern communities played an important role in improving the environment. Their roots began holding the soil together again. Their leaves reduced the direct impact of rain on the ground. Dead plant material slowly mixed into the soil and increased its ability to hold water and nutrients. Small animals found shelter beneath the growing vegetation. Tiny insects fed on leaves and plant remains. Fungi and bacteria broke down dead material and returned nutrients to the soil. These simple communities marked the beginning of larger ecosystems that would continue developing over millions of years. Mosses and liverworts also contributed to the recovery of the land. These small plants could grow on exposed rocks, damp ground, and disturbed soils. They helped trap moisture and reduce the movement of loose sediment. Although they remained close to the ground, they supported small organisms that formed the base of recovering food webs. Their presence showed that life was slowly returning, even in places where conditions remained difficult. As time passed, seed plants began expanding once more. These plants had an advantage because their seeds protected young plants during early development. Seeds could remain inactive until conditions became suitable for growth. Some could survive dry periods that would have killed more delicate plants. This ability allowed seed plants to spread into regions where the climate remained uncertain. Among the important seed plants were early conifers. These trees gradually became some of the most successful plants during the Triassic period. Many conifers had leaves that reduced water loss. Their strong trunks supported taller growth, allowing them to reach sunlight above smaller plants. Their seeds were carried by wind or other natural processes into new areas. As forests slowly returned, conifers became major parts of many woodland ecosystems. Seed ferns also survived the extinction, although many groups suffered severe losses. They had characteristics of both ferns and seed-producing plants. Instead of producing spores like true ferns, they produced seeds while keeping leaves that often resembled fern leaves. Some seed ferns recovered during the early Triassic and formed part of developing forests. Other groups continued declining until they eventually disappeared much later. Another important group included cycads. These plants had thick trunks and large leaves growing from the top. They were well suited to warm climates and became common in many Triassic environments. Cycads produced seeds and formed an important source of food for some plant-eating animals. Their sturdy structure allowed them to survive in conditions that were difficult for many other plants. Binet Italians also appeared during this period. These seed plants looked somewhat similar to cycads, but belonged to a different group. They spread across many regions and became important parts of Triassic vegetation. Their reproductive structures were more complex than those of many earlier plants. Although they eventually disappeared millions of years later, they were successful members of recovering ecosystems during much of the Triassic. Ginkgos also appeared as part of the recovering plant world. Their fan-shaped leaves are well known today because one living species still survives. Ancient ginkgos formed part of forests in several regions. Their ability to survive changing climates helped them remain successful through many geological periods. The return of forests happened slowly because trees require stable conditions to become established. Young trees need enough water, suitable temperatures, healthy soil, and time to grow. After the extinction, many of these conditions were unreliable. Climate changes continued for long periods. Hot temperatures affected large areas. Rainfall varied greatly from place to place. Some regions experienced long dry seasons while others received heavy rain, followed by drought. Trees growing under these conditions often struggled to survive. Volcanic activity continued for a long time after the extinction. Huge eruptions released carbon dioxide and other gases into the atmosphere. These gases affected temperatures around the world. Ash from eruptions covered landscapes in some areas. Fresh volcanic rock created new surfaces, where plants eventually began growing. Although volcanic activity caused great destruction, it also created new land that later supported recovering ecosystems. Carbon dioxide levels remained much higher than many earlier periods. High carbon dioxide sometimes increased plant growth when enough water was available. However, extreme heat and water shortages often limited these benefits. Many plants experienced stress because the environment remained unstable. Some species adapted while others disappeared. The recovery of soils was one of the most important parts of rebuilding ecosystems. Healthy soil contains minerals, water, air, fungi, bacteria, insects, worms, and decaying organic material. After the extinction, many soils lost much of their organic content because forests had vanished. Without constant additions of leaves, branches, and roots, soil quality declined. Recovery required countless generations of plants growing, dying, and adding material back into the ground. Fungi played a major role during this recovery. These organisms broke down dead plants and animals, releasing nutrients that new plants needed. Some fungi formed close partnerships with plant roots. The fungi helped plants absorb water and minerals while receiving food from the plants. These relationships greatly improved plant survival in damaged environments. Bacteria also became essential members of recovering ecosystems. Some bacteria broke down organic material, while others helped recycle nutrients such as nitrogen. Without these microscopic organisms, plant growth would have been much slower. Although they rarely leave obvious fossils, scientists know they played important roles because modern ecosystems depend heavily upon them. As plants spread across the land again, insects gradually became more common. Many insects survived the extinction despite severe losses. Plant-eating insects fed on leaves, stems, seeds, and wood. Other insects fed on fungi or dead organic matter. Predatory insects hunted smaller insects. These activities helped rebuild food webs that had nearly collapsed during the extinction. Evidence of insect feeding appears on fossil leaves from Triassic rocks. Scientists study holes, bite marks, tunnels, and scars preserved in fossil plants. These traces show that insects returned to feeding on plants relatively early during ecosystem recovery. Different feeding styles became more common as plant diversity increased. Plant reproduction slowly became more successful as ecosystems stabilized. Wind carried pollen between plants over wide areas. Some insects may have assisted certain plant groups, although wind remained the main method for many species. Successful reproduction allowed forests to expand from scattered patches into larger connected regions. The first recovering forests were usually less diverse than the forests that existed before the extinction. Many areas contained only a few dominant tree species. This reduced diversity reflected the severe losses caused by the extinction. Over millions of years, additional plant groups appeared, increasing the variety found within forests. The structure of recovering forests also differed from earlier forests. Younger forests often had fewer layers of vegetation. The tallest trees formed an upper layer, while smaller plants covered the ground. As ecosystems matured, shrubs, climbing plants, and different tree sizes created more complex habitats. Greater complexity allowed more animals to live within the forests. Water played a central role in determining where forests recovered first. River valleys often supported richer vegetation because they provided steady moisture. Floodplains allowed plants to grow even during dry seasons. Lakesides also supported recovering plant communities. Areas far from dependable water sources often remained open landscapes for much longer periods. Mountain regions showed different recovery patterns from lowland areas. Higher elevations usually experienced cooler temperatures and different rainfall. Plant communities changed according to altitude, soil type, and local climate. Some mountain valleys became safe places where surviving plant species continued growing, while surrounding regions remained damaged. Coastal environments also experienced slow recovery. Salt levels changed as sea levels rose and fell. Coastal swamps, river mouths, and shallow wetlands gradually supported new plant communities. These habitats became important breeding and feeding areas for many animals as ecosystems expanded. Wetlands recovered through the growth of ferns, horsetails, mosses, and other water-loving plants. Standing water allowed many species to survive periods of drought. Organic material collected in these wetlands, creating rich soils that supported larger vegetation. Wetlands also provided homes for amphibians, reptiles, insects, and many small organisms. The return of forests influenced the atmosphere itself. Growing plants absorbed carbon dioxide during photosynthesis and released oxygen. Although this process occurred slowly over millions of years, expanding forests gradually affected the balance of gases in the atmosphere. Plant growth also influenced local temperatures by providing shade and increasing moisture released from leaves. Plant roots changed the movement of water through the landscape. Water entered the ground more easily, where roots created channels within the soil. This reduced surface runoff and helped refill underground water supplies. Streams became more stable because plants slowed the movement of rainfall into rivers. These changes improved conditions for aquatic life. The rebuilding of ecosystems depended upon countless interactions among plants, animals, fungi, bacteria, and the physical environment. No single species restored ecosystems alone. Every living organism contributed in different ways. Small changes accumulated over long periods until stable communities became established. Plant-eating reptiles benefited from the gradual increase in vegetation. As forests expanded, more leaves, seeds, stems, and roots became available as food. Herbivorous animals spread into recovering habitats and influenced plant communities by eating certain species more than others. Their waste returned nutrients to the soil, supporting further plant growth. Carnivorous reptiles followed plant-eating animals into recovering ecosystems. Predators helped regulate herbivore populations. This balance prevented some plant communities from being completely consumed. Predator and prey relationships gradually became established once again across recovering landscapes. Small mammals had not yet become major parts of Triassic ecosystems, but the earliest mammal relatives and other small vertebrates lived among the vegetation. They found shelter beneath fallen branches, inside burrows, and among dense plant growth. These small animals fed on insects, seeds, and other available food sources. Amphibians remained closely connected to water. Wet forests, ponds, rivers, and marshes supported many surviving amphibian groups. Thick vegetation protected moist environments that these animals required for survival. Their eggs usually needed water, making healthy wetlands especially important. The first true forests after the extinction varied from place to place because Earth's continents were joined together in the giant supercontinent called Pangaea. This enormous landmass influenced climate across much of the world. Interior regions were often very dry because they lay far from the oceans. Coastal regions generally received more rainfall. Plant communities reflected these differences. Large deserts occupied many inland regions during the Triassic Period. Plants growing there developed ways to reduce water loss and survive dry conditions. Forests remained limited near dependable water supplies. River systems crossing dry landscapes became centers of biological activity because plants concentrated around available moisture. Seasonal rainfall also shaped recovering ecosystems. Some areas experienced long dry seasons, followed by periods of heavy rain. Plants adapted by growing rapidly during wet conditions and slowing growth during dry months. Seeds often remained inactive until rainfall returned. These seasonal patterns influenced the timing of reproduction and growth throughout ecosystems. Scientists learn about these ancient forests by studying fossil leaves, wood, pollen, spores, seeds, roots, and tree trunks preserved in rocks. Petrified wood provides detailed information about tree structure. Growth rings sometimes reveal changing climate conditions. Fossil pollen and spores help identify plant species even when larger plant remains are missing. Coal deposits also provide valuable evidence. Large coal beds formed from accumulated plant material in wet environments. The absence of extensive coal deposits immediately after the extinction suggests that large swamp forests remained rare during the earliest stages of recovery. Later coal deposits show that richer plant communities eventually returned in some regions. Fossil root systems reveal how ancient plants interacted with soils. Scientists examine the depth, branching patterns, and distribution of roots to understand environmental conditions. Deep roots may indicate access to underground water, while shallow roots sometimes reflect poor soils or frequent flooding. Plant fossils from different continents help scientists reconstruct global recovery patterns. Similar species found across distant regions indicate that many plants spread widely because the continents remained connected. Local differences also reveal how climate and geography influenced vegetation. Changes in pollen preserved within rock layers provide one of the clearest records of recovery. Certain pollen types become abundant as particular plant groups expand. By studying thousands of pollen grains under microscopes, scientists trace changes in forests over long periods. These tiny fossils often survive even when larger plant remains have disappeared. Ancient river deposits preserve evidence of recovering vegetation. Fossil logs buried by floods show where forests once stood. Leaves trapped in river sediments provide detailed records of local plant communities. Mudstones and sandstones containing plant fossils help reconstruct ancient landscapes. The recovery of ecosystems did not happen at the same speed everywhere. Some regions regained forests earlier because local conditions remained favorable. Other areas stayed open and sparsely vegetated for millions of years. Climate, water supply, volcanic activity, soil quality, and surviving plant populations all influenced recovery rates. Many plant lineages that survived the extinction became the ancestors of groups that dominated later parts of the Triassic. Their success created habitats where early dinosaurs, crocodile relatives, insects, reptiles, and many other organisms eventually lived. Forests supported growing biodiversity by providing food, shelter, nesting places, and protection. The rebuilding of ecosystems also influenced nutrient cycles. Leaves falling from trees added organic matter to the soil. Microorganisms broke down this material and released nutrients. Plants absorbed these nutrients through their roots. Animals consumed plants and returned nutrients through waste and decomposition after death. These repeating processes gradually became stable again as ecosystems matured. Different plant species occupied different habitats according to their needs. Some preferred wet ground beside rivers. Others grew on dry hillsides. Certain plants thrived in disturbed areas where floods or fires created open spaces. This distribution increased the overall diversity of recovering ecosystems. Wildfires probably continued affecting some Triassic landscapes because dry climates remained common. Fires removed old vegetation, but also created open ground where new plants could grow. Some plant species recovered quickly after fire through seeds or underground structures. Fire therefore became one natural factor, shaping vegetation patterns in many regions. Storms, floods, droughts, and changing temperatures continued influencing forests throughout the Triassic. Plant communities constantly adjusted to these environmental conditions. Species unable to adapt gradually disappeared from some areas, while better adapted plants expanded into available habitats. The first forests after the Great Extinction were not identical to those that had existed before the disaster. They represented new combinations of surviving plant groups that gradually filled empty ecological roles left behind by extinct species. As millions of years passed, these forests became richer and more stable, supporting increasingly complex ecosystems across the recovering world. Around 252 million years ago, the Triassic period began after the largest mass extinction known in Earth's history. Life on land and in the seas had gone through a time of great loss. Many kinds of animals and plants had disappeared forever. The land looked very different from what it had been before. Large areas were dry, and the climate in many places was hot for much of the year. Rivers, lakes, forests, and open plains slowly became home to new groups of living things. Over many millions of years, animals and plants spread into places that had become empty after the extinction. During this long period of recovery, a small group of reptiles slowly appeared that would later become known as the first dinosaurs. The earliest dinosaurs did not suddenly appear in large numbers. Their story began through a long process of change that took place over many millions of years. Each generation passed small changes to the next. Some of these changes helped animals survive better in the places where they lived. Animals with useful features were more likely to stay alive, find food, avoid danger, and produce young. Over a very long time, these small changes built up until new kinds of animals appeared. The earliest dinosaurs were one result of this slow process. The world of the early Triassic was still recovering from the Great Extinction. Many habitats had fewer living things than before. Forests slowly returned to many regions. Rivers carved new paths across the land. Seasonal rains filled lakes and streams before dry weather returned. Plants that could survive heat and changing weather spread across large areas. Ferns, seed ferns, conifers, horsetails, and several other groups became common in many places. These plants provided food and shelter for many kinds of animals. The continents were joined together as one huge landmass called Pangaea. Since most of the land was connected, animals could travel over great distances without crossing wide oceans. This allowed many groups of reptiles to spread across different regions. Some animals lived near rivers and lakes, while others survived in dry plains or forests. Weather conditions changed from place to place, but many areas experienced long dry seasons, followed by periods of rain. The ancestors of dinosaurs belong to a larger group of reptiles, known today as archosaurs. This group also included the ancestors of crocodiles and several other reptiles that lived during the Triassic period. Archosaurs first appeared after the Great Extinction and quickly spread across many environments. They developed many different body shapes and ways of life. Some became hunters, others ate plants. Some were small enough to hide among thick plants, while others grew much larger. Early archosaurs showed many features that later became important in dinosaurs. Their legs were placed more directly under their bodies instead of spreading far out to the sides. This body plan helped support their weight more effectively and allowed smoother movement. Walking and running became easier because their bodies stayed more balanced while moving. This was an important step toward the body design seen in the first dinosaurs. Scientists have spent many years studying fossils from rocks formed during the Triassic period to understand how dinosaurs first appeared. Fossils preserve the bones, teeth, footprints, eggs, and sometimes even skin impressions of ancient animals. Every new fossil discovery helps scientists understand more about the early history of dinosaurs. Fossils are often found after rocks become exposed by rivers, wind, rain, or human work such as road building and mining. Careful digging allows scientists to remove fossils without damaging them. Many of the earliest dinosaur fossils have been found in South America. Countries such as Argentina and Brazil contain rocks that formed during the late Triassic. These rocks have preserved some of the oldest known dinosaurs and many close relatives. Fossils from these places have helped scientists build a clearer picture of how dinosaurs first evolved. One of the earliest known dinosaurs is Eoraptor. Its name means dawn thief because it lived near the beginning of dinosaur history. Eoraptor lived about 231 million years ago in what is now Argentina. It was a small animal measuring about 1 meter in length and weighing only several kilograms. Its body was light and it could move quickly on 2 legs. It had long legs, sharp claws, and a long tail that helped keep its body balanced while moving. The skull of Eoraptor contained many sharp teeth that suggest it could eat small animals, insects, and perhaps some plants. Scientists continue to study its teeth because they show features linked with different groups of early dinosaurs. This makes Eoraptor especially important for understanding how the first dinosaurs developed. Another early dinosaur was Herrerasaurus, which also lived in what is now Argentina around 231 million years ago. Herrerasaurus was much larger than Eoraptor. It could reach several meters in length and had powerful legs that allowed fast movement. Its jaws contained many sharp teeth designed for catching and eating meat. Strong arms ended with large claws that could help hold struggling prey. Herrerasaurus showed that some early dinosaurs had already become active hunters. Although later meat-eating dinosaurs became much larger, Herrerasaurus already displayed many important features that would continue in later dinosaur groups. Scientists have carefully studied its skeleton because it helps explain how the earliest meat-eating dinosaurs were built. Another important early dinosaur was Saturnalia from Brazil. Saturnalia lived around 225 million years ago. It was relatively small with a light body and long neck. Scientists believe it mainly ate plants, although it may also have eaten small animals at times. Saturnalia is important because it belonged to the group that later produced the giant, long-necked dinosaurs, known as sauropods. During its own lifetime, however, Saturnalia remained much smaller than its later relatives. The first dinosaurs shared several features that made them different from many earlier reptiles. Their hips had a special structure that supported efficient movement. Their legs stood beneath their bodies instead of spreading outward. Their ankle bones formed joints that allowed steady walking and running. Many early dinosaurs also had long tails that helped maintain balance during movement. Their bones contained spaces that reduced weight while keeping strength. The earliest dinosaurs were generally small animals. Most stood no taller than an adult person, and many were much smaller. Their size allowed them to move through forests, across riverbanks, and over open ground while searching for food. Small body size also meant they needed fewer resources than much larger animals. Being small did not mean they were weak. Many had strong muscles attached to their hips and legs. Their feet were built for active movement. Some species probably spent much of the day searching for food over large areas. Their sharp eyesight may have helped them find prey or detect danger. Their sense of smell may also have helped locate food and recognize other members of their own species. The first dinosaurs did not immediately become the most common animals on land. For many millions of years, they lived alongside many other reptiles. Several groups of archosaurs remained very successful during the Triassic Period. Large crocodile relatives filled many hunting roles. Plant-eating reptiles also spread widely across different environments. Dinosaurs remained only one part of these ecosystems for a long time. Scientists think that dinosaurs slowly increased in number because several features helped them survive changing conditions. Their upright posture allowed efficient movement over long distances. Their bodies may have supported active lifestyles. Some evidence suggests they grew relatively quickly compared with several other reptiles living at the same time. Faster growth could have allowed young dinosaurs to reach adulthood sooner and begin producing young earlier. The climate of the Triassic often changed between wet and dry periods. Animals living during this time needed to survive changing temperatures and changing food supplies. Dinosaurs that could travel greater distances may have found new food sources when local supplies became limited. Their strong legs helped them move across different kinds of ground, including river valleys, forests, and open plains. Early dinosaur eggs were laid in nests on land. Although very little direct evidence survives from the earliest dinosaurs, later dinosaur fossils show that eggs had hard shells that protected the developing young. Adult dinosaurs probably selected places where the eggs could remain safe from flooding and some predators. After the young hatched, they had to survive in a world filled with many dangers. Young dinosaurs faced threats from larger reptiles, meat-eating animals, floods, droughts, disease, and shortages of food. Only a small number likely survived to adulthood. Those that did survive continued the line that slowly spread across different regions of Pangaea. Scientists study fossil bones under microscopes to understand how quickly early dinosaurs grew. Thin slices of fossil bone show growth rings, and tiny structures formed while the animals were alive. These studies suggest that several early dinosaurs grew faster than many reptiles living during the same period. Faster growth may have helped them recover from injuries, become adults sooner, and increase their chances of survival. The first dinosaurs also developed many different feeding habits. Some mainly ate meat, others mainly ate plants. A few may have eaten both plants and animals depending on what was available. Different diets allowed various dinosaur species to live in the same regions without relying on exactly the same food. Fossil footprints provide another important source of information about early dinosaurs. Ancient footprints preserved in soft mud later hardened into rock. These tracks show how dinosaurs walked, how fast they moved, and whether they traveled alone or in small groups. Some trackways suggest steady walking, while others indicate running. The spacing between footprints helps scientists estimate the length of each step and the speed of movement. As more fossils continue to be discovered in South America, Africa, India, North America, Europe, and other parts of the world, scientists keep improving their understanding of how the earliest dinosaurs first appeared. New discoveries sometimes confirm earlier ideas and sometimes lead researchers to revise them as fresh evidence becomes available. The story of the first dinosaurs continues to grow as each fossil adds another piece to the record of life during the Triassic Period. The Triassic Period was a time when life on Earth was changing after the greatest mass extinction in the planet's history. The living things that survived faced a world that was very different from the one that had existed before. Many older groups of animals had disappeared forever, leaving behind empty places in nature. These empty places allowed new kinds of reptiles to grow, spread, and become important parts of life on land, in rivers, along the coasts, and in the seas. During this long period, dinosaurs first appeared, but they were only one part of a much larger collection of reptiles. Many other reptiles lived beside them, hunted them, competed for food with them, or shared the same forests, deserts, rivers, lakes, and shorelines. The Triassic world was filled with many kinds of reptiles that had different shapes, different sizes, different diets, and different ways of living. The reptiles of the Triassic came from groups that had survived the great extinction that happened before the beginning of the period. These survivors carried features that allowed them to live in difficult conditions. Over many millions of years, they slowly changed through evolution. Small differences that helped them survive were passed on to their young. As generation followed generation, these changes became greater. New groups formed, and many of them spread across the huge supercontinent known as Pangaea. Since most of the land was joined together, many reptiles could travel across wide areas without crossing large oceans. This allowed many species to spread over great distances. The climate of the Triassic was often hot and dry across much of the land. There were deserts that stretched across large regions. There were also rivers, lakes, seasonal wetlands, forests, and coastal areas where plants could grow more easily. Different reptiles adapted to different places. Some preferred dry open land where they could move quickly. Others stayed close to rivers where food and water were easier to find. Some became strong swimmers, while others remained land animals throughout their lives. One of the most successful groups during the Triassic belonged to a larger branch of reptiles called archosaurs. This group included the ancestors of dinosaurs, crocodiles, flying reptiles, and several other important reptiles. Archosaurs became some of the most successful animals after the Great Extinction because they had body features that helped them move well, breathe efficiently, and survive in changing environments. Over time, different branches of archosaurs developed into very different animals. Among these reptiles were early relatives of crocodiles, often called crocodile-line archosaurs. These animals looked very different from the crocodiles that live today. Some had long legs that lifted their bodies high above the ground instead of keeping them close to the earth. Many could run much faster than modern crocodiles. Some walked on 4 legs, while others could move on 2 legs for short periods or even most of the time. Their bodies showed many different forms because evolution was exploring many ways of living. Some crocodile relatives became large hunters. They had long jaws filled with sharp teeth that could grip struggling prey. Their strong neck muscles helped them hold animals firmly while biting. Their eyes were placed where they could watch for movement across open land. Instead of waiting quietly in rivers like many modern crocodiles, some Triassic crocodile relatives actively chased animals across dry ground. They hunted early mammals, smaller reptiles, amphibians, and sometimes young dinosaurs. Other crocodile relatives became plant eaters. These reptiles had teeth better suited for cutting leaves, stems, and other plant material. Their bodies became wider, and their heads often changed shape to help them gather vegetation. This showed that even closely related reptiles could survive by eating completely different foods. Some members of this group developed heavy armor, made from bony plates inside their skin. These plates protected them from attacks by hunters. The armor also helped support their bodies. Different species had different patterns of armor. Some had rows running down their backs, while others had larger plates covering more of their bodies. This protection made them harder for predators to injure. One well-known crocodile-line reptile was Postosuchus. It lived during the later part of the Triassic and became one of the largest land predators of its time. It had powerful jaws, long legs, sharp teeth, and a strong body. It hunted many kinds of animals that shared its environment. Although dinosaurs were beginning to spread, animals such as Postosuchus were still among the leading hunters in many regions. Another important group of Triassic reptiles included etosaurs. These animals were heavily armored plant eaters. Their bodies were covered with thick rows of bony plates that formed a natural shield. Their heads were usually smaller than their bodies, and many had short snouts. They spent much of their time searching for food near the ground. Some probably dug into soft soil using their snouts to uncover roots, insects, and other food. Others fed mostly on low-growing plants. Their heavy armor protected them from many predators. Etosaurs lived across many parts of Pangaea. Fossils have been discovered in areas that are now found on different continents. This wide distribution shows that these reptiles successfully spread across large regions, while the continents remained connected. Different species adapted to local conditions, but they all shared the protective armor that made their group easy to recognize. Another unusual group was the Rauisuchians. These reptiles included several large predators with powerful bodies. Many had long legs that allowed them to move efficiently across land. Their skulls held large openings that reduced weight while still remaining strong. Their jaws carried sharp teeth designed for holding flesh. These animals occupied important hunting roles before dinosaurs became the largest land predators. The success of Rauisuchians showed that dinosaurs did not immediately take over every environment after they first appeared. Instead, many different reptile groups lived together for a long time. Some groups became common in certain places, while others dominated different habitats. Nature supported many kinds of reptiles at the same time. Phytosaurs formed another remarkable reptile group during the Triassic. At first glance, they looked much like modern crocodiles, because they had long bodies, strong tails, and long jaws filled with teeth. However, they were not true crocodiles. One noticeable difference was the position of their nostrils, which were located close to their eyes rather than at the end of the snout. This feature shows that they belong to a separate branch of reptile evolution. Phytosaurs spent much of their lives in rivers, lakes, and wetlands. They waited for fish, amphibians, and animals that came close to the water. Their bodies allowed them to swim effectively. Their powerful tails pushed them through the water, while their eyes remained above the surface to watch for prey. Their sharp teeth helped hold slippery animals. Some phytosaurs grew very large. Their size alone made them dangerous hunters. Young reptiles, early dinosaurs, amphibians, and fish all faced the risk of becoming food if they entered waters where phytosaurs lived. These reptiles became some of the most successful freshwater predators during much of the Triassic. Another interesting group included the ornithosuchids. These reptiles had unusual body shapes and could move in different ways depending on the situation. Some evidence suggests they could sometimes walk on two legs. Their jaws contained curved teeth that helped them grip prey. They probably hunted smaller animals and may also have fed on dead animals when opportunities appeared. There were also smaller reptiles that lived quietly beneath larger animals. Many fed on insects, spiders, worms, and other tiny creatures. These small reptiles played important roles by helping control insect populations and serving as food for larger hunters. Although their fossils receive less attention than giant predators, they formed an important part of Triassic ecosystems. Prolacertiform reptiles represented another branch that produced long-necked species with flexible bodies. Their necks helped them reach food in different places. Some caught small animals hiding among plants or rocks. Others searched for insects and other small prey. Their light bodies allowed quick movement through vegetation. Tanystropheus became one of the most unusual reptiles of the Triassic. It possessed an extremely long neck supported by elongated bones. Most of its body remained relatively ordinary in size, making the neck its most striking feature. Scientists continue to study exactly how it lived. Fossil evidence suggests that it spent time near water, where its long neck may have helped it catch fish or other small animals, while keeping much of its body farther away. Despite its long neck, Tanystropheus had a sturdy skeleton. The neck bones were not numerous, but instead were greatly lengthened. This unusual structure made it different from many other reptiles. Its body shows that Triassic evolution produced many body forms, while reptiles adapted to different ways of finding food. Dinosaurs formed another successful plant-eating reptile group. These reptiles had broad bodies, strong limbs, and beak-like mouths that helped them crop tough vegetation. Their powerful jaws contained teeth suited for grinding plant material. They became especially common in several Triassic environments where plants formed abundant food supplies. Large groups of rhynchosaurs may have moved together while searching for vegetation. Living in groups could have reduced the chances that individual animals would be attacked. Their strong jaws allowed them to feed on plants that some other reptiles found difficult to eat. Fossils suggest they were among the most common plant eaters in certain regions during parts of the Triassic. Early turtles may also have begun developing during the later Triassic. Some fossil reptiles from this time show features that appear related to the earliest stages of turtle evolution. Their shells were not yet fully developed as seen in modern turtles, but parts of the skeleton suggest that the protective shell slowly evolved over time. This process involved changes to ribs, backbone, and other bones. The appearance of early turtle relatives shows that reptile evolution followed many different paths at once. While some reptiles became fast runners, others developed armor, long necks, powerful jaws, or swimming bodies. Each group responded differently to the environments where they lived. Flying reptiles also appeared during the Triassic. These reptiles, known as pterosaurs, were not dinosaurs even though they lived beside them. They became the first vertebrates to achieve powered flight. Their wings were supported mainly by an extremely long fourth finger that stretched a thin skin membrane. Strong muscles connected the wings to the body, allowing controlled flight. Early pterosaurs were generally smaller than many later species that lived during later periods. They hunted insects, fish, and other small animals. Some flew above rivers and lakes searching for prey. Others hunted in forests or along coastlines. Their ability to fly allowed them to reach food sources unavailable to land animals. The arrival of flying reptiles added another layer to Triassic ecosystems. Food was no longer gathered only on land or in water. The skies also became home to reptiles. This opened new opportunities while creating new relationships among animals. Flying reptiles sometimes escaped predators by taking to the air, although young individuals still faced danger from hunters before they could fly well. Marine reptiles also flourished throughout the Triassic oceans. These reptiles returned to the sea after their distant ancestors had lived on land. Their bodies gradually changed to suit aquatic life. Legs transformed into paddles, tails became stronger for swimming, and many developed streamlined bodies that reduced resistance while moving through water. Ichthyosaurs became one of the best-known marine reptiles. Their bodies were shaped for fast swimming. They hunted fish, squid-like animals, and other sea creatures. Large eyes helped them see underwater, even in deeper or darker conditions. Some species gave birth to live young instead of laying eggs on land. This adaptation allowed them to spend their entire lives in the ocean. Nothosaurs represented another marine reptile group. Unlike ichthyosaurs, they often spent time both in water and near shorelines. Their long necks and sharp teeth helped catch fish. Their limbs allowed movement both in water and on land, although they swam much more efficiently than they walked. Platodonts developed yet another way of living in the sea. Many fed on shellfish and other hard-shelled animals. Their broad, flat teeth crushed shells before swallowing the soft parts inside. Some placoodonts developed wide bodies with protective armor that gave extra defense against predators. These marine reptiles filled many roles in Triassic oceans. Some hunted fast-moving fish. Others searched along the seafloor for shellfish. Some lived in shallow coastal waters, while others spent more time in deeper seas. Their success showed that reptiles had become important animals both on land and in the oceans. Freshwater environments also supported many reptiles. Rivers and lakes attracted animals because they provided drinking water, plants, fish, amphibians, and shelter. Large predators often waited near water sources where other animals gathered. Smaller reptiles searched along muddy banks for insects and tiny prey. Eggs laid near water had better chances of surviving in some environments because moisture remained available. Seasonal rainfall strongly influenced many Triassic reptiles. During wet seasons, rivers expanded and plants became more abundant. Food supplies increased, allowing animals to grow and reproduce. During dry seasons, water became scarce. Many reptiles traveled longer distances, searching for water and food. Some species adapted by surviving with limited resources until wetter conditions returned. Reptiles also developed many different methods of protecting themselves. Armor became common in several groups. Others depended on speed to escape danger. Some used camouflage provided by skin colors and patterns that blended with rocks, soil, or plants. Large body size discouraged attacks from smaller predators. Sharp teeth, claws, and strong jaws also served as defenses. Reproduction remained an important part of reptile success. Most Triassic reptiles laid eggs with protective shells. These eggs could survive outside water better than amphibian eggs. Parents selected nesting places that reduced danger from flooding or predators. Some buried eggs beneath soil or sand. Others may have covered nests with plants. Evidence for direct parental care remains limited for many Triassic reptiles, but protecting eggs through careful nesting likely increased survival. Young reptiles faced many dangers. Eggs could be eaten by predators before hatching. Newly hatched reptiles were small and vulnerable. Birds had not yet become important predators because they had not evolved, but many reptiles hunted young reptiles. Fish, amphibians, insects, and larger reptiles all threatened hatchlings. Only a small number survived long enough to become adults. As reptiles matured, their diets often changed. Young individuals usually ate smaller prey because of their size. Larger adults could hunt bigger animals or consume tougher plants. Growing bodies required increasing amounts of food. Fast growth helped reduce the period during which young reptiles remained vulnerable. The spread of forests also influenced reptile life. Forests offered shade, shelter, nesting places, insects, fruits from seed plants, and hiding places for prey. Tree roots stabilized soil, while fallen leaves supported many small animals that reptiles could eat. Open forests differed from dense forests, allowing different reptile species to occupy different habitats. Deserts created separate challenges. Water remained scarce, temperatures changed greatly between day and night, and food could be difficult to find. Reptiles living in these regions developed behaviors that helped conserve water. Some remained inactive during the hottest parts of the day. Others searched for food during cooler morning or evening hours. Burrows provided protection from heat and helped retain moisture. Coastal environments supported their own reptile communities. Beaches, tidal flats, lagoons, and river mouths attracted fish and other animals. Reptiles living near coasts often had access to both marine and land food sources. Seasonal storms could reshape these habitats, requiring animals to adapt continuously. Competition existed among many reptile groups. Different predators sometimes hunted the same prey. Plant eaters searched for similar food sources. Competition encouraged changes over many generations, as species adapted to different diets, habitats, or behaviors. Some reptiles specialized in particular foods, while others remained flexible and ate many different things depending on availability. predator and prey relationships shaped evolution throughout the Triassic. Faster prey encouraged predators to become quicker. Stronger defenses encouraged stronger jaws or sharper teeth. Better camouflage reduced successful attacks. Improved senses helped hunters locate prey, while helping prey detect approaching danger. The senses of Triassic reptiles varied according to their lifestyles. Hunters often possessed forward-facing eyes that improved judgment of distance. Aquatic reptiles relied on vision and sensitivity to water movement. Plant eaters often had wide fields of view that allowed them to watch for approaching predators while feeding. Smell also played an important role in locating food, finding mates, and recognizing danger. Brain development differed among reptile groups. Some had brains suited mainly for basic survival behaviors. Others showed evidence of improved coordination, needed for active hunting, swimming, or flying. As different lifestyles evolved, nervous systems adapted to meet new demands. The skin of Triassic reptiles also varied. Most possessed scales that reduced water loss and protected the body. Scale size and arrangement differed among species. Armored reptiles added thick bony plates beneath the skin. Some aquatic reptiles had smoother outer surfaces that improved movement through water. Color cannot usually be determined directly from most fossils, but many scientists believe Triassic reptiles probably displayed a range of natural colors. Browns, greens, greys, blacks, and other earth tones may have helped them blend into their surroundings. Some species may also have displayed brighter markings during mating seasons or while communicating with others of their own kind. The end Triassic mass extinction was one of the most important events in the long history of life on Earth. It happened at the very end of the Triassic Period, about 201 million years ago. During this time, many different kinds of living things disappeared from the planet. The event affected life on land, in the oceans, and in freshwater environments. Many groups of animals and plants faced serious problems, and a large number of species could not survive the changing conditions. After this extinction, the Earth entered the Jurassic Period, and the world of living things became very different from what it had been before. Before this extinction took place, the Earth was already changing in many ways. The continents were still joined together in the giant landmass called Pangaea, although it had started to break apart. Large cracks formed in the Earth's crust, and these openings allowed huge amounts of molten rock to rise from deep inside the planet. This volcanic activity became one of the most important causes of the environmental changes that followed. The eruptions did not happen in a single day or even in a single year. They continued over a long period, releasing enormous amounts of lava and gases into the atmosphere. Scientists have found evidence of these volcanic eruptions in a region known today as the Central Atlantic Magmatic Province. This area covers parts of what are now North America, South America, Europe, and Africa. Thick layers of hardened lava spread across huge areas of land. Even after more than 200 million years, these rocks remain as clear signs of the volcanic activity that took place during the end of the Triassic Period. The volcanoes released large amounts of carbon dioxide into the atmosphere. Carbon dioxide is a gas that helps keep heat around the Earth. When its amount increases, the average temperature of the planet can rise. The continuous release of this gas caused the climate to become warmer over time. Higher temperatures affected plants, animals, rivers, lakes, and oceans. Living things that had adapted to earlier conditions suddenly faced a world that became harder to survive in. The volcanic eruptions also released sulfur gases into the atmosphere. These gases could react with water in the air and form acidic rain. Acid rain changed the chemistry of lakes, rivers, and soils. Some plants found it difficult to grow under these conditions. Trees and other land plants depended on healthy soil, clean water, and stable weather. When these conditions changed, many plant communities suffered. The volcanic eruptions also filled the atmosphere with tiny particles of ash and dust. These particles blocked part of the sunlight from reaching the Earth's surface. Less sunlight meant cooler conditions for short periods after some eruptions. Plants depend on sunlight to make food. Reduced sunlight slowed their growth. Animals that depended on plants also faced food shortages. After the dust settled, the large amounts of carbon dioxide already released into the atmosphere continued to increase temperatures. This meant that the Earth experienced changing conditions over time instead of remaining stable. Scientists believe that the repeated cycle of volcanic eruptions, cooling from volcanic particles, and warming from greenhouse gases placed great pressure on many ecosystems. Living things often survive gradual changes, but repeated changes happening over a relatively short period made survival much more difficult. Some species could not adjust quickly enough. Their numbers became smaller until they finally disappeared. The oceans also experienced major changes during this period. As the atmosphere became warmer, the surface waters of the oceans also warmed. Warm water holds less dissolved oxygen than cooler water. Many sea animals depend on oxygen in the water to survive. As oxygen levels dropped, some parts of the oceans became difficult places for marine life. Scientists have found rocks from this period that show signs of low oxygen levels in ancient seas. These rocks contain chemical clues that help researchers understand what happened long ago. They suggest that many parts of the oceans became poor in oxygen for long periods. Animals living on the seafloor and swimming in open water were affected by these conditions. Some scientists also think that warming oceans changed the movement of water around the world. Ocean currents help move heat, nutrients, and oxygen from one place to another. Changes in these currents could have created areas where oxygen became even lower. Marine animals living in these places faced serious problems. The increase in carbon dioxide also changed the chemistry of seawater. When carbon dioxide enters the ocean, it reacts with water to form weak acids. Over long periods, this process can make seawater more acidic. Many marine animals build shells or skeletons from calcium carbonate. More acidic water makes it harder for these animals to produce and maintain their shells. Young animals are often especially sensitive to these changes because their shells are still developing. Corals were among the marine organisms affected during this extinction. Coral reefs support many kinds of sea life. Fish, shellfish, and many other marine animals depend on reef environments for food and shelter. When reefs declined, many species lost the habitats they needed for survival. Many kinds of shell-forming animals also disappeared. Some groups that had lived successfully for millions of years were greatly reduced. Others became completely extinct. Fossils from rocks formed before and after the extinction clearly show that many marine species vanished during this time. Ammonoids were another group that suffered greatly. These sea animals had coiled shells and were related to modern squid and octopuses. They had survived earlier environmental changes, but lost many species during the end Triassic extinction. Only a small number survived and later gave rise to new species during the Jurassic period. Conodonts were another ancient group that disappeared completely during this extinction. These small eel-like animals had existed for hundreds of millions of years. Scientists know them mainly from their tiny tooth-like fossils, which are common in many ancient rocks. Their complete disappearance marks one of the important biological changes at the end of the Triassic. On land, many reptiles that had once been common also disappeared. During the Triassic period, dinosaurs were only one part of a much larger group of reptiles. Many other reptiles filled different habitats and ways of life. Some looked similar to crocodiles, others had long legs for running. Some were large plant eaters, while others hunted smaller animals. Many of these groups became extinct during the end Triassic event. The extinction created empty habitats across many environments. These empty places later became available for surviving groups of animals. Dinosaurs happened to survive much better than many of their reptile relatives. As the Jurassic period began, dinosaurs spread into many of the habitats that had once been occupied by extinct groups. Scientists continue to study why dinosaurs survived, while many other reptiles disappeared. Several ideas have been suggested. Some researchers think that dinosaurs may have been better able to cope with changing climates. Others believe they reproduced more successfully or had physical features that allowed them to survive difficult environmental conditions. There is still active research on this question, and no single answer explains every detail. Many large amphibians also suffered during the extinction. Amphibians depend heavily on water for reproduction and survival. Changes in rainfall, river systems, lake conditions, and temperature created difficult environments for these animals. Some groups became extinct while others experienced large declines in their populations. Plants also experienced important changes during this period. Fossil pollen and spores preserved in ancient rocks provide evidence of changing plant communities. Some plant species disappeared completely. Others became much less common. Forests changed as different kinds of plants replaced earlier vegetation. Wildfires may have become more common because warmer climates and changing rainfall created dry conditions in many regions. Charcoal preserved in ancient rocks shows that fires occurred in some parts of the world during this period. Large fires destroyed forests and changed habitats for many animals. Changing rainfall patterns also affected freshwater environments. Rivers changed their paths. Some lakes became smaller or dried up. Other lakes developed different chemical conditions. Fish, amphibians, insects, and freshwater plants all depended on stable water supplies. As these environments changed, many freshwater species struggled to survive. Some scientists have found evidence that mercury levels increased in rocks formed during this period. Volcanoes release mercury along with other gases. Ancient rocks containing higher mercury levels support the idea that widespread volcanic activity played an important role in driving environmental changes. Researchers study fossils from many different parts of the world to understand how the extinction unfolded. Fossils from Europe, North America, South America, Africa, Asia, and other regions all show evidence that many species disappeared at roughly the same time. Although conditions varied from place to place, the overall pattern points to a global event rather than a local disaster. Dating ancient rocks has become much more accurate over the years. Modern methods allow scientists to estimate the ages of volcanic rocks and fossil-bearing layers with much greater precision than in the past. These studies show that the timing of the massive volcanic eruptions closely matches the timing of the extinction. This close connection strengthens the idea that volcanic activity was the main driving force behind the environmental crisis. The extinction did not remove every species. Many plants and animals survived. These survivors formed the basis for later ecosystems during the Jurassic period. However, survival often meant living through changing temperatures, changing rainfall, lower oxygen levels, damaged habitats, and reduced food supplies. Even species that survived may have experienced major declines before their population slowly recovered.